All right, good morning, everyone. So start off with a couple of announcements. So we have decided to move the exam from Monday to Wednesday, just because we lost those 2 days there. So anyways, so we decided to move it there. So instead of Monday being the second exam, it's going to be Wednesday. So we'll meet tomorrow. So again, tomorrow, as it says up there, will also probably be virtual, because I'm assuming my son's school will still be closed tomorrow. We found some friends to drop him off at to get him out of the house a little bit for today, but that's not going to happen tomorrow too. So unfortunately, so tomorrow will probably be virtual. I'll send out Zoom invitations for that later. Other than that, the homework then will be postponed from Sunday night then to Tuesday night. So I'll give you a couple more days to work on that as well, which means all the group assignments and extra credit and all that stuff will also be due on those days. So hopefully we'll be able to finish off most of the material by tomorrow, and then Monday we'll tie up some loose ends, and then basically the rest of the day we'll do a review, and I'll give you all the group assignments basically then. And so I'll give you a couple days to work on all that good stuff. So that's about it. So let's do one more example, and then we'll move on to some other types of forces and things that we're going to see. So this example is what's known as an Atwood machine. So basically what I have here is this is a massless and frictionless pulley. Has a cord then strapped from M1 here, which is 5 kilograms, down to M2, which is then 4 kilograms, and then has a second cord, which then goes from M2 to M3, where M3 is then 3 kilograms. So in this round, what we want to know is what is the acceleration of the system, and then finally, what is the tension in the cords? So first of all, I know this cord here is the same as this cord, so these two have exactly the same tension, but there's a second cord here, which means that we're going to have 2 different tensions in this case. So what I want to know then is what are all of the accelerations, and then what are all of the different tensions. So this is what we want to know. Now again, by Newton's third law, what we know is that the acceleration of this guy will be the same as this guy, which will be the same as this guy. Now on here, since I have 5 kilograms on this side, 7 kilograms on this side, we can safely assume this guy is going to accelerate upward, while this one's going to accelerate down, and this one is also going to accelerate downward. It's more people. There we go. Now, the next thing is, instead of working with a problem like this, we can actually do a modified version of this problem. And the reason for that is, as far as the acceleration is concerned, let's look at M1 here. M1 knows it's being pulled up because there's some mass on this side. M1 here doesn't care if it's being pulled up by M2 and M3 separately. All it cares is that it's being pulled up by a total amount of mass of M2 plus M3. So an easier way to do this problem is, instead of writing a free body diagram for everything, we'll do a simplified version of the problem, which means I'm just going to collapse these two into a single mass. Because as far as M1 is concerned, it doesn't care that it's 2 separate masses. All it cares is the total mass between the two. So in that case, I'm going to use that to find the acceleration, and then pull it apart to find the individual tensions. So instead of doing this, we're going to instead do this. This is still going to be M1. On this side, I'm now going to call this M4, where M4 is the same thing as M2 plus M3. So in this case, this is going to be a total of 7 kilograms. So we're going to analyze this problem instead. Where again, this guy's going to accelerate upward, and this guy's going to accelerate downward. Now from here, this is now just a connected body problem, which we've done a whole bunch of times now. So again, what we have to do is draw a free body diagram for this mass, draw a free body diagram for this mass, use a different coordinate system here and here. We'll have then 2 equations, 2 unknowns, solve those 2 things simultaneously to find the acceleration. And then again, we can get the tensions in there. So let's go ahead and do that. So let me draw a free body diagram for M1, a free body diagram for M4. So Ethan, give me a force on M1.
Tension.
Tension, good. Which way is tension? Upward. Call that T1 for now. Harrison, give me another force on M1.
Gravity.
Gravity, good. So you got the gravitational force, M1G. Teddy, any other forces on M1? No, that's it, good. So here, we know this guy's going to accelerate upward. So I'm going to go ahead and choose my positive y to be upward. Now, before I analyze that, let's work on the other one. So, Dane, can you give me a force on M4?
Gravity.
Gravity, which way?
Down.
straight down. So got an M4G here. Good. And Paige, what's the other force on M4? Tension. The same tension as that one or different one? Same. Good. So also upward, T1. And this guy's going to accelerate downward. So in this case, I'm going to choose positive Y to be downward. So again, these two guys can have completely different order systems. So good. So from here, I'm just going to apply the second law on this guy. So I'm going to say that some of the forces in the Y direction. Is it accelerating in the Y? Yes. So this becomes M1A. So where am I? Brooke, give me a force in the Y direction.
Tension.
All of it or part of it?
All of it.
Positive or negative?
Positive.
Positive. It's going to be a T1. Ruth, give me another one on M1 in the Y direction.
Gravity.
All of it or part of it?
All of it.
Positive or negative?
Negative.
So here I get T1 minus M1G is equal to M1A. So this one says that as I can find the acceleration if I know the tension. I don't know the tension. Where's the tension going to come from? My other block. So let's look at the other block. Now I can say for this one, I have the sum of the forces in the Y direction. Is that guy accelerating? Yes. This is going to be an M2A. So Jair, give me a force in the Y direction.
Negative tension.
Negative tension, good. So in this case, it's negative tension because tension is in the opposite direction as the positive Y direction. Very good. And Briston, what's the other one?
M4G gravity.
What? Positive or negative?
Positive.
All of it or part of it?
All of it.
Now, this one says I can find the acceleration again if I know the tension. So good. So again, we have two equations. This is equation number one. This is equation number two. Again, however you want to solve this is completely up to you. Here I can solve this for T1, plug that back into over here. I personally am lazy, so I like to just add these two guys together, noticing that this is a positive sign, that's a negative sign. The two are just going to cancel. It's a little easier that way. So let's go ahead and do that. So let's add them together. So I go T1 minus M1G equal to M1A plus a negative T1 plus M4G is equal to M4, sorry, that should be M4. M4A. Add these guys together. Again, the T1s are going to cancel because they are one's positive, one's negative. So this gives me finally an M4 minus M1 times G is equal to M1 plus M4 times A. Finally, solve this for the acceleration. It says the acceleration then is equal to M4 minus M1 divided by M1 plus M4 all times G. Plug in my numbers. This is 7 minus, what, 5? So this is 2 divided by 7 plus 5, which is 12, times G. So this works out to be 1.63 meters per second squared. So this is my acceleration of the system. Okay. About 1/6 the size of gravity. So good. So now that we have the acceleration, now we need the tensions. So with this acceleration, how do we find the tensions? Well, here we already have two equations which both have T1 in it, so I can just plug it into either one of these two. Doesn't matter which one, whichever one is your favorite one. All we're going to do is plug acceleration into here and then simply find T1. So let's do that. Brooke, which one's your favorite one?
The first one.
The first one. Good. Sounds good. So here, I'm just going to get a T1 that is equal to an M1G plus M1A, which is then going to be M1 times G plus A. So it's going to be M1, which is 5 kilograms, times 9.8 plus 1.63, which then works out to be about 57.15 newtons. So this is T1. Okay? So the question is now, how do I find T2? Well, to find T2, I now have to go back in to look at this and see what this actually came from. So this thing actually came from, let's redraw our picture, two masses, which was M2, connected then to M3. But again, I know the acceleration of each one of those. The acceleration of each one is the same as the acceleration we just found. So we now know this one's accelerating downward, this one is also accelerating downward. So here, to find now the second tension, which we're going to call T2, I'm now just going to redraw a free body diagram for him and him. So let's go ahead and do that. So now, get rid of this one. Get rid of this one. So now let's do a new free body diagram for M2 and a new free body diagram for M3. So, okay. Maria, give me a force on M2. Tension, which one? Okay, and which one is that going to be? Is that going to be T1 or T2? T1, good. So here, we now have T1 going upward. What else do we have in there? Jarrett, what other forces do I have in M2? Gravity, we got that pulling down. So I got M2G. Now back to you, Ethan, sorry, we're a smaller class today. So,
The second tension.
the second tension, which way is the second tension pointing?
Downward.
Downward, good. So this one, T2, is now pulling downward. Now again, we know the acceleration is downward, so we could draw our positive y to be downward. Simultaneously, let's look at M3. So, Harrison, give me a force on M3.
T2.
T2, which way is T2 now? Upward, good. T2 up. And Dane, what's the last one? Gravity. So I got M3G. And again, acceleration is downward. Choose our positive y direction again to be downward. Now, from here, let's think about what we know. We know M2G, we know T1 now, we know A, the only thing we don't know is T2, which means we could use this free body diagram to find T2. Or we can use this one because we also know actually we don't know T2, but we know the acceleration and we know M3G. So we can use this one to then find T3. Whichever one you want to use, it doesn't matter. We can either use this diagram or this diagram. They give me the same information because those two T3s are the same. Personally, I would use this one because it has the least amount of crap. So let's use this one. So here I would just add how many forces that in my y direction is equal to M3G. And now this is specifically M3. So here, gravity's pulling downward, that's positive, so I get an M3G minus T2 is equal to M3, oops, sorry, M3A. So solve this for T2, this gives me M3 times G minus A is then equal to T2. Plug in that, this works out to be about 25.51 newtons is equal to the second. Doing okay? So not bad. So again, the nice thing about forces is everything is very systematic. The bad thing about forces is there's no one single expression for anything. So there is no single expression for tension, no single expression for normal force, no single expression for anything. Every problem you have to redefine what all of these things are based off of the geometry. But the nice thing is, since it's so systematic, it's nice and easy, you can easily go through and do it. It's not too difficult. So next thing we're going to talk about is another type of force. We're not going to do too much with this force, but we're going to talk about it anyways. And this force is what happens when you move through a fluid. So what's a fluid? So first let's define a fluid. So for now, we'll redefine what a fluid is later, but a fluid is for now, a substance which flows. So this is going to be a rough definition of what a fluid is. So fluid is anything that flows. So what does that mean? There's air in this room. Does the air flow? It's a fluid. there is water in here. Does that flow? That's a fluid. Anything that flows, therefore, is a fluid, which means that this thing is not. This would be a solid. So what happens is, anytime I have an object which is moving through a fluid, I get a type of force on this object, which is called the drag force. So whenever an object moves through a fluid, the object has a force on it due to the collisions the object makes with the fluid itself. So basically what happens is, as my object is moving through the fluid, which is what I'm doing right now because I live in air, I have the molecules in the air slamming into me as I'm trying to move through the fluid. As I move through it, the faster I move through it, the more collisions I make. The more collisions I make increases the amount of force onto me. Right? This is what happens when you drive your car, for example. Just kind of barely going down the road, you can put your arm out and do one of these. Life is great. What happens if you do this at about 60 miles an hour? You rip your damn shoulder up. It's basically what will happen. Right? So if you're driving down the road, you put your arm out the window at 60, 70 miles an hour, that force on your arm is huge. It's going to rip your arm right out. So the faster we go, the more collisions we make with the fluid, which causes us to move at a slower rate. This is why when you actually drive faster, you burn more fuel. And the reason for that is to move at constant speed at a faster rate, the force which is being pushed on you by the air is much greater. You have to overcome that force by applying your constant force, which means that you're burning gas at a much quicker rate. This is usually why most roads, you see the speedometer or the speed limit is more like 55. It's not because they're trying to save lives, it's because they want to save gas. If you die, that's fine. If we lose gas, we got a problem. So, other ways I can see this is how we move through this fluid also depends on the shape of the object. So, as this thing is actually falling through, if I took my piece of paper and I drop it like this, I have a whole amount of drag force acting onto this. This thing has a very large cross-sectional area. As this thing is falling down, it has a large cross-sectional area, so there's a lot of drag force on this object. If I took it, instead put it this way, in that case the drag falls pretty quickly. Or if I took it and I crumple it up, doesn't even act like the drag force is actually here. So the way that drag works is it depends on basically the shape of the object. In general, there are two different types of drag forces. There's a drag force which goes linearly with the velocity of the object, and there's another drag force which goes basically quadratic with the velocity. Typically, one is more dominant over the other one depending on how fast it's going. So when you're moving at slow speeds, the linear drag force is actually more dominant than the quadratic drag force, which is why when you're driving at slow speeds, you put your arm outside and it doesn't break your shoulder out. But then once you break a particular threshold, which is usually around 35 miles per hour, you then go from the linear drag up to the quadratic drag. At that stage, the force becomes much bigger because now it's quadratic in the velocity. So the faster that you're moving, that drag force becomes huge. Now, why does this happen? Well, again, this happens because with the linear drag force, as I'm trying to move through the fluid, I'm trying to push that fluid out of the way, which means I have to accelerate the fluid in front of me out of the way to be able to move through the fluid. This is where the linear drag force comes from. The quadratic drag force comes from the fact that if I'm moving too fast, the fluid then becomes what's called turbulent. What turbulence means is, basically, here's my object moving through the fluid. The fluid basically starts building up and kind of doing little swirlies behind the object itself. What it does is it actually creates a pocket. That pocket, you then have to drag with you as you're moving down. Any of you ever dragged off the back of a semi before? can actually do this on a highway. So if you're driving in a highway, you can actually get your car right here into this pocket. You'll actually have a force from the fluid sucking back into the back of the semi, dragging your car with it. So you can actually take your foot almost off the gas and actually have the semi drag you down the road instead of you wasting all your gas. So the faster that you're going, not only are you trying to accelerate this fluid out of the way, but now you have a big pocket of fluid being dragged with you behind, which then causes a much larger amount of drag force onto your vehicle. So this is what the drag force is. Now, for us, the only one that we're going to be interested in is the quadratic version. We're going to be mostly interested more in high speeds. So let's talk about drag force. So the magnitude of the drag force is equal to 1/2 of the density. So this is the density of the fluid. Times C, where C is what's known as the drag coefficient, times the area, so this is the effective cross-sectional area, times the velocity squared. Or in this case, actually the speed squared. Now, what's the direction of this force? This direction is always opposite to the direction of the velocity. So the direction, so F drag direction is opposite to the direction of the velocity. So meaning that if this was my object, moving, say, in this direction with a velocity v, my drag force would be exactly in the opposite direction. So this would be my drag force. So it's always opposite of the direction of the motion. Which means that if I took this ball, right, and I throw it upward, on the way up, the drag force is pointing downward. But then when it turns around and moves back down, the drag force now becomes upward. So it's always opposite the direction of its actual motion. So this is the drag force. So let's talk a little bit more about these things. So what does the effective cross-sectional area mean? So that goes back to this piece of paper. When I dropped it like this, the effective cross-sectional area then is the entire area of the paper. But when I dropped it like this, the reason it moved much faster is because now my effective cross-sectional area is this line. So as I change the cross-sectional area, I can also change the amount of drag. You've seen this in movies all the time. Right? When the damsel falls out of the airplane and the hero has to go jumping out of the airplane to go get her. Right? So what happens? She's falling, doing something like this. And how does he catch up to her? That's right, he tucks and put his head down. Right? Reason for that is now he's decreased his cross-sectional area from his entire body to now just effectively his shoulders. So now he has a much smaller cross-sectional area, which allows him to move much faster. Then when he catches her, then he does one of these to make himself as big as possible to then reduce his speed. We'll see what that actually looks like in a second. So this is drag force. Now, what he's doing when he's moving at a higher speed versus lower speed is he has reached what's known as terminal velocity. What terminal velocity means is if I took this ball and I went way up and I dropped it, what will eventually happen is as this thing is falling down, we know it has an acceleration of gravity act down to it, which means its velocity gets bigger, 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 bigger. As that velocity gets bigger and bigger and bigger and bigger, what happens then is the drag force gets bigger and bigger and bigger. The weight stays the same. So eventually what's going to happen is the drag force will equal in magnitude to that of the gravitational force. At that point, this goes now into a static system. There is no more acceleration. This thing falls at a maximum rate, which is called the terminal velocity. So the terminal velocity any object can reach is when the acceleration goes to 0. So let's talk about terminal velocity. Terminal velocity. This is the maximum speed an object can reach when the acceleration is equal to 0. So okay, what do I mean by that? So this is my ball. My ball starts to fall. We know this thing has a gravitational force acting downward. So we got mg acting this way. And as this thing is falling, the drag force is now going to build up in this direction. So that, let's say initially, its acceleration is downward. So my positive y direction. So in this case, I'm going to get an mg minus my drag force is equal to m. Now, since the drag force is proportional to the velocity, actually the velocity squared, what happens then is this thing reaches its maximum velocity when, again, the acceleration goes to 0. So in this case, v goes to the terminal when the acceleration goes to 0. So let's find the maximum velocity that this guy can jump out of the airplane. So again, let's say that he's trying to save his wife as she's plummeting to the ground, and he dives after her. So let's use this. So when the acceleration goes to 0, I then have that mg is equal to drag, which is now equal to 1/2 the density times the coefficient times the area times then the terminal velocity squared. What I want to know is, what is that terminal velocity? So we can multiply by 2, divide by all that stuff, and take a square root. So this has the terminal velocity that is twice the mass times g, divided by rho c a squared. So this then would be our terminal velocity for somebody jumping out of the airplane. This is the maximum speed at which he could go. Out of curiosity, what would happen if the guy jumped out of an airplane with a speed greater than his terminal velocity? So let's say she was really going to die. She was like, maybe 100 meters off the ground. So instead of jumping out, he shot himself out of a cannon out of an airplane. What would happen to his speed as he was then plummeting downward? Would he be able to maintain a speed greater than that of the terminal velocity? No. Right. What would happen in that case is if he came out with a higher velocity, what would happen then is that the drag force would actually be much bigger than the gravitational force, which means he would actually be slowing down as he's falling instead of speeding up, until eventually what will happen again is that the drag force will equal the weight, at which point he would reach that exact same terminal velocity. So regardless of what his initial velocity was, if we look at his velocity as a function of time, if this was the terminal velocity here, you would asymptote to that terminal velocity regardless of his initial velocity. So this is the greatest amount that he could reach under natural circumstances. Now let's go back to here. So what we said was that if he jumped out head first, he would go at a faster rate than what he would if he was spreading out, like a spread eagle. Can we see that here? Does this make sense? Does that go along with what it was that we said? Good, Teddy, why?
Because they're on opposite sides. The areas on the bottom. So
Exactly, because the area is on the bottom. So if he makes his area as small as possible, this makes a smaller denominator, which makes this whole real number bigger. Right? Whenever I have a small denominator, that makes the number larger. Then when he opens up, he makes a large cross-sectional area. That makes the denominator bigger, which then makes this a much smaller. Exactly. So this actually matches exactly what it was that we said. Let's do another example. So let's find what's the terminal velocity that a bicyclist can reach. Or sorry, a skier. So here I have a downhill skier is skiing with a drag force acting on him. And he also has a coefficient of friction between his skis and the snow. So let's draw a picture of what's going on. So here is my slope. And we at some angle, I think it was 20 degrees, up 40 degrees. Here's my skier, so here's the skis. Here's my skier. Beautiful skier. And let's say that here, between the snow and his skis, is a coefficient of kinetic friction, which is equal to 0.04. He's got a drag force acting on him. His mass is equal to 85 kilograms. His coefficient of drag is equal to 0.15. And let's say he's moving in air with the density of air is equal to 1.2 kilograms per meter cubed. And finally, let's say he has a cross-sectional area which is equal to 1.3 meters squared. So what I want to know is, as this guy is accelerating down the hill, is again drag force is going to build up on top of him. So what I want to know is, in this case, what's the terminal velocity? How fast can this skier go down this slope? So this is what we want to know. So to do this, we do the same thing as always. Let's draw a free body diagram. My man is a block. There's my skier. Makes my life easier. So what forces are acting on my skier? Where did I start? Teddy, I think I was on you, right? Give me a force on the skier. Force of gravity. Good. Which way is that? Straight down. So in this case, we got mg down. Paige, give me another one.
Normal.
Normal force. Good. Which way is the normal force?
Parallel or perpendicular.
Good. Perpendicular to the surface. So that's my normal force. Brooke, give me another one.
The drag.
The drag. Which way is the drag going to be?
To the right, like angle.
Good. So up the plane, because he's moving down the plane. Good. So my drag force is going to be this one. And Ruth, there's one more. I'll give you a hint. There's a coefficient of kinetic friction. Good. That's right. Friction force up the plane. Very good. So our kinetic friction up the plane. Good. Exactly. Now, for now, I'm going to say his acceleration is down the plane, even though we're looking for the terminal velocity, which means we're eventually going to take that acceleration equal to 0. Okay? But in this case, just so I can set up my coordinate system. So since the acceleration is down the plane, I'm going to call this my x direction. Call this my y direction, which forces this to be the same angle as x. Oh, good. Now here, since there is a kinetic friction, what that means is we're going to need to know what the normal force is. Because remember that kinetic friction is equal to the coefficients times the normal force. Right? So in this case, we are going to have to work with both the sum of the forces in the x direction and in the y direction. So let's go ahead and do that. So let's do sum of the forces in the x and the sum of the forces in the y. Show you which direction you want to do. X or Y?
X.
X first. Good. Is he accelerating in the X direction?
Yes.
Yes. Again, for now. We're going to take it to 0 later, but for now, yes. Good. Kristen, give me a force in the X direction.
The friction.
The friction, good. Positive or negative?
Negative.
All of it or part of it?
All of it.
That's it. Okay, good. Maria, give me force in the X direction. Drag force, all of it or part of it? Positive or negative? Good. And Jarrett, what's the last one? Art of gravity, good. Positive or negative? Positive, good. And which part? Always the tricky part. So remember, we're looking at this part here. So is that the opposite of that angle or the adjacent? Looking here. That's the opposite. Good. And opposite always goes with? Side. Very good. Now, since we have this kinetic friction here, which we know is mu sub k times the normal force, that means we should now jump to the sum of the forces in the y direction. Let's go ahead and do that. So is he accelerating in the y direction? No. Good. So automatically I know that's 0. Sorry, either we're back to you again. So give me force in the y direction. All over department?
All of it.
Positive or negative?
Positive.
Good. And Harrison?
Part of gravity.
Part of gravity? Positive or negative?
Negative.
Good. And which parts?
Cosine.
Cosine. Good. Is equal to 0. Good. So good. So from the y direction, we have the normal force that is equal to mg cosine of theta. And all we're going to do is take that and then substitute that in here for the friction force. Again, the friction is mu sub k times the normal force. So let's do that. So this becomes minus mu sub k mg cosine of theta minus my drag force plus my sine portion of the weight is then equal to ma. So this is my expression. Now from here, again, what we want is the terminal velocity. And we now know that the terminal velocity occurs when the acceleration goes to 0. So what we're going to do here is we're going to take this acceleration here, set it equal to 0, and then write this in terms of the terminal velocity. Okay? Now, let's do that. So I'm going to set this side equal to 0. Now, since terminal velocity is inside of the drag force, I'm first going to solve this for the drag force. So I'm just going to add the drag force to both sides. So let's do that. So let's solve the drag force. This is F drag then is equal to mg sine of theta minus mu sub k mg cosine of theta. Now let's use our drag force. So we know this is 1/2 the density times the coefficient times the area times the terminal velocity squared, then is equal to all that stuff. Finally, what we want is simply the terminal velocity. So I'm going to multiply both sides by 2, divide by all the extra stuff, and take a square root. This will be our terminal velocity. So finally, we get the terminal velocity is equal to the square roots of 2 times mg times sine of theta minus mu sub k cosine of theta, all divided by 0. Somebody. I tried to go back.
Hey, am I tripping, or should the cosine be on the with the x and the sine should be with y?
Oh, so good question. So again, we're looking at this triangle here. So remember, x doesn't always go with cosine. It just means how does it relate to there. So since I'm looking at this triangle here, this is my hypotenuse of the triangle, and for here I'm looking for this part here. Right? So this is mg. Now, according to this angle is here relative between the y-axis and the hypotenuse, which means that this portion is the opposite side of here. So that's right. So here, this is actually mg sine of theta because it deals with the opposite side. Exactly. And on this side, so this is the adjacent side to this angle, which means that this mgy then is the mg cosine of theta. So for these problems, it actually works opposite to what you'd usually expect it to be. So
How do you know what side to look for? Like, is it just...
So all that just depends on, for example, what direction you're doing the sum of your forces in. Is that kind of what you mean? Or that's right. So the other way to think about it is here, since I want everything in the x direction, I'm looking for this portion of the vector which points this way. So this is the portion which points along the x direction. The hardest thing here is mostly to kind of convince yourself that this angle here is the same as this angle here. So once you kind of bring yourself to that, it's not too bad. And again, when I'm looking in the y direction, what I'm looking for here, I'm looking for this vector which points down in this direction. That one just points this way. So the y I'm looking for this portion. Then I get that from the angle. So your answer to your question is no, you're not tripping. But it's just kind of more ingrained with you that cosine should be x and y should be sine. So Yeah, so here we just have to be a little bit careful where those angles actually are. Is it okay? What's up, Maria?
Can you repeat why the acceleration is 0?
Oh, because we specifically want the terminal velocity. So it happens to go to terminal velocity every time the acceleration goes to 0. Okay. Anywhere up till that point, it's actually going to be exponentially increasing. So what happened is, in this case, if I plotted the velocity versus time, it's actually going to do something like this, where this is actually going to be a hyperbolic tangent. So basically it's exponential. So what happened is, if I look at the velocity as time goes on, this thing is going to start off basically at 0, kind of increase linearly, and then kind of increase exponentially, and then basically go to a constant at that stage. That's a later stage. And I'll give you a hint. This is actually your outside of extra credit for it. Showing me that. Great.
I have a question.
Sure.
How do you know in the x direction which one is negative and which one is positive?
Say that one more time.
You have in the x direction, right? That side is positive and
Yep.
the other side is negative.
Correct.
How do you know that?
Oh, I took that because what I was saying is if he starts up here, he's going to slide down. So what I know is at any time point up until when he reaches terminal velocity, his acceleration will be down the plane. So from there, I just chose that the positive x direction was in the direction of the acceleration. That's my choice. Doesn't have to be your choice, it's just, that's what I chose. Now, the reason I do that, going back to what we talked about before, is I have to remember that the sum of the forces equal to the mass times the acceleration, that this guy is a vector. So if in this case, let's back up a little bit, if I chose this as my positive x direction, in this case, the acceleration would actually be negative. Okay? So in that case, when I wrote this out, I would have to write mass times negative the acceleration. So I have to make sure I take that negative sign into account. Because my acceleration is now opposite to the direction of what I chose as the positive x direction.
It will be easier if we decide to put the x positive.
That way I never have to forget about that negative sign. Exactly. That's basically the reason why I do that. So I just make these two in the same direction, so that way I don't ever have to worry about that negative sign. Always okay? Stop working.
So like whenever you did the sideways like XY system,
Ah.
and you said like the theta would be the same as the 40, is it always going to be like that, or will there be like an example where it would change?
Good question. Yes, is the answer to that. Give you an example. This is going to deal with something we're going to talk about tomorrow. Okay. But let's say I had an object here, and I chose instead of this as my positive x direction, I chose this as my positive x direction. Okay. So let's work with that. So if I work with this one, this is now my positive y direction. So now, for example, I'm going to have my normal force pointing off in this direction. So the question now is, what angle is which? Okay. So what I know is that ultimate interior angle, so this angle here is the same as this angle, so this is the angle theta, which means that I extend this off in this direction. Let's see here. So this one goes this way. This one then is also theta, which means that this one is also theta here. Which by extension, which means when I have mg pointing down in this direction, and I take this coordinate system, so this is y here, this is what forces this guy to be theta. Okay. So let's see here, where was I going with that? Okay, so no, I think it's still right, because in the y direction, this would still be cosine, and in the x direction, this would still be sine. So never mind. So the answer to that is no, actually. So it would still actually work out to be the same. So yeah, so I think that'd still be fine. Yeah. But this is your answer to why this angle is the same as this, and the same as this, and the same as this. All of our ninth grade geometry or whatever that stuff like that. But no, so even in this case, if I chose a regular coordinate system, then this angle here would work out to be the same as the way that this one is. So here, if I was looking at this portion of the normal force, for example, this would be n normal force y, so that would be the normal force times cosine of theta. And then this portion here would be normal force x, so that would be the normal force times sine of theta. So in that case, no. So the answer is, yeah, it would always work out that way whenever it's tilted. Okay? Questions? All right, one more thing to talk about for today. And this is the idea of what's known as equilibrium. So let's quickly talk about equilibrium. So what's equilibrium? So equilibrium just simply means that the velocity is equal to a constant. This is what we call equilibrium. So for us, whenever the velocity is equal to a constant, what does that tell us about the acceleration? Velocity is equal to a constant, what's the acceleration? Zero. Zero, good. So this means our acceleration is equal to zero, which means the second law simply becomes sum of forces equal to zero. So equilibrium is also what we call statics. All it means is that something is either moving with constant speed or it's not moving at all, which is also constant speed, right? So how do I know this? Well, I know this thing is sitting here, it's moving at constant speed. How do I know it's moving at constant speed? What are you doing right now? You're sitting. What was the Earth doing? Rotating. What else is it doing? It's rotating about the sun. So it's rotating about its axis, it's rotating about the sun. And what else is it doing? It's expanding outward, which means it's also moving in the linear sense as well. So even though right now you see this thing as not moving because you think you're not moving, you are actually also moving with constant speed. Which means that there is no distinction between this thing not moving and this thing moving as long as it's moving or not moving at a constant rate. This is what we call equilibrium. So equilibrium basically just means the sum of your life is equal to zero. Nothing happens. It's about as boring as possible. This is civil engineering. So, how do we deal with problems like this? Well, basically, we'll be given problems where things will be not moving, and we'll have to decide things like tensions and all kinds of other stuff. So let's say I give you a problem that looks like the following. So let's say here I have a sign. Here is my traffic sign connected to one cord, which is then connected to two other cords. Something like this. Where here, I'm going to tell you that this angle here, well, that's theta 1, is equal to 37 degrees. This angle here, theta 2, this is then equal to 53 degrees. And let's say the mass of the sign here is equal to 10 kilograms. So for this problem, we want to know simply, what are all the tensions? This is the way statics basically works. So, how do we do this problem? Well, to do this problem, we have to use a little bit of a trick here. Because how many different chords do I have here? Good, I have 3 chords, right? Which means I don't know this tension, I don't know this tension, I don't know this tension, which means mathematically, how many equations do I have to know to be able to get rid of 3 unknowns? Good, 3, right? For every number of unknowns I need an equation. Now, if I simply look at the sum of the forces in the x and y direction, how many equations am I going to have? 2. Which means I'm not going to technically have enough equations to be able to solve this. So the way we're going to do a problem like this is we're going to actually isolate this into 2 parts. First, we're going to look at this part and look at the sum of the forces on him. And then secondly, we're going to isolate this part here and then look at the sum of the forces here. So basically, where these 3 chords meet each other, we're going to treat it as an object and then do the sum of the forces there. So here what's going to happen is all the forces are acting in one direction, so that gives me 1 equation. But here, I'm going to have forces in 2 directions, which means I have sum of the forces in each one of those 2 directions, which gives me a total number of 3 equations. So in things like this, we have to get a little bit tricky where we have to actually break this thing up and then look at this part here, even though it's not a physical mass, it's not a physical object, we're going to treat it like an object. And then for this part here, this is an actual object with an actual tension here. Now, we don't have time to do that right now, so we'll have to do that tomorrow. So we'll pick up and actually analyze the system tomorrow. And then after that, we'll talk about why I brought the rest of this here, which is what's known as centripetal forces. So centripetal forces are forces which cause things like this to move in a circle. Now, one thing I will point out about centripetal forces, which I will talk about in depth tomorrow, there is no such thing as a centripetal force by itself, which means there has to be a real physical force causing something to move in a circle. So for example, when this bucket is moving in a circle, what is the centripetal force for this bucket? So what is causing this bucket to move in a circle? The force in the string, right? The tension. How do I know that? Because if I do that, it breaks it, right? It goes flying off in different directions. So one thing that's always going to be true in centripetal forces is there's no such thing as a centripetal force by itself, which means I don't walk down the road and then get spun around in a circle for no reason and say, damn, that centripetal force got me. Unless I'm drunk. All bets are off if I'm drunk. Okay, so we'll talk more about this tomorrow. So I'll see you guys tomorrow. So yeah, tomorrow will more than likely be virtual. Thank you. I'll post off links and everything for that later today. See you later, Preston. Where's my stop button?